Good afternoon. My name is Todd Giddings, and I'm a hydrogeologist who has been studying the Spring Creek Watershed in Center County for more than 50 years. 2018 being the wettest year in 122 years of record provided an unusually strong opportunity to understand the recharge capacity of the watershed. Looking at 88 years of total annual precipitation, the horizontal red line of 40.66 inches represents a 30-year average, and at the top right corner of the graph, 63.75 inches were received in 2018, which is more than 50% above the average amount. Looking at the 30-year average as compared to the excess rainfall, this shows that the excess is greater than 50% of the 30-year average, and within that excess rainfall, groundwater storage increased by about 12 inches, which again is more than half of the excess. This groundwater storage increase caused the water table throughout the watershed to rise 66.3 feet, and that represents 36 billion gallons of groundwater. The base flow was more than 27 inches, and that represents 68% of the total flow from the watershed during 2018. On a monthly basis, the green bars show that the least precipitation month of February is above 2 inches, and the wettest month, August, is just above 4 inches. So there's a very uniform distribution of the 30-year average monthly rainfall. Superimposing the precipitation from 2018, we see that the greatest precipitation month with more than 9 inches of rainfall was July, and it more than doubled the average. And every month through the end of 2018 received significantly above average rainfall. The recharge to the water table is shown by this rise in the water table level, and it started out about 110 feet below ground level and rose to less than 40 feet above ground level for a total rise of 66 feet. And this represented 36 billion gallons. Looking ahead into 2019, we see from the water level hydrograph that the groundwater recharge stayed within the watershed significantly into the following year. The Karst characteristics of the Spring Creek Watershed include groundwater piracy from the adjacent Spruce Creek Watershed. This makes the groundwater watershed area 23% larger than the surface water watershed area. We have the Gatesburg Formation with a very high level of effective porosity, giving us significant groundwater storage, and it is the headwaters area of Big Spring and Bellefonte that's flowing at 14 million gallons a day, which makes it the second greatest flowing spring in all of Pennsylvania. We have a typical mountain runoff into sinkholes in the carbonate valley floor at the foot of the mountain ridges, and we have streams carrying the mountain recharge out onto the valley floor to distribute it further away from the ridges. A non-typical karst characteristic is our very large area of high infiltration capacity soils, so that contributed significantly to swallowing the excess rainfall in 2018. On this oblique aerial photograph, the star orients you with Beaver Stadium. So State College is in the valley floor area that I'm outlining. And the boundary of the watershed on the west follows Bald Eagle Ridge, and on the east side follows Tussey Mountain Ridge. The yellow shaded area represents the carbonate rock valley floor area, and each of the light blue arrows shows you a mountain stream, and at the point of each arrowhead is generally a sinkhole that will swallow part or all of the stream flow, recharging the carbonate aquifer area. Each double red circle represents a public water supply well or well field, and our total daily groundwater withdrawal pumpage is 16 million gallons per day. The blue shaded area represents the difference between the surface water boundary and the groundwater watershed boundary, and the white arrow is showing you the direction of the streams in the Spruce Creek surface water watershed area that are flowing away from the Spring Creek watershed. Underlying this area is the Birmingham Thrust Fault that is a groundwater flow conduit to Big Spring and Bellefonte, and that's the area where groundwater piracy from Spruce Creek is occurring. This area is a principal reason why the average groundwater base flow in the Spring Creek watershed is more than 85% of total flow. This photograph shows you the height of a solution opening that's following the Birmingham Thrust Fault and carrying the groundwater flow 15 miles from the headwaters to Big Spring Pool. The double white arrow is a cross-sectional view that will show you in the next slide the groundwater piracy. It has a typical watershed surface water boundary where surface water flows into the Spring Creek watershed and the Spruce Creek watershed. The second and more important boundary is the groundwater flow boundary, which is shown by the red bracket as being several miles beyond the surface water boundary of the Spring Creek watershed. So that a drop of water, if it ran overland, it would be in the Spruce Creek surface water watershed, But if this drop of water infiltrates to the subsurface and becomes groundwater, it's taken by the flow along the Birmingham Fault to discharge at Big Spring and Bellefonte. And that's the principle of groundwater piracy. The white line represents a stream carrying mountain runoff out onto the floor of the valley, and the star symbol is a recharge sinkhole area located within the stream channel. We're going to look at two observation wells, 118, that'll be a red line, and 686, that'll be a black hydrograph line. And these two observation wells are only 2.3 miles apart on the valley floor, and therefore they're receiving essentially the same amount of precipitation derived recharge. Here's 20 years of total annual precipitation shown by the blue bars, and the black line is the hydrograph of well 686 that typically follows wet years in terms of shallow depth below ground level, here less than 40 feet, and then follows dry years by showing a greater depth below ground level. This red line is the hydrograph of well 118, and you can see that the peak highest level in 118 lags behind 686 by about 6 months due to it receiving distributed recharge out on the valley floor. If we look at this 3 units of hydrograph rise in well 686 and compare it to this distance of water table rise in well 118, this 3-to-1 ratio means that we have in the formation surrounding well 118, the red line, 4.5% effective porosity, which is 3 times the average porosity throughout the rest of the Spring Creek watershed. The shaded tan area represents the high infiltration capacity soils that were so effective in absorbing the excess rainfall during 2018. The red oval shows you the area we're going to take a closer look at of the distributing stream flowing from mountain recharge on Tussey Mountain out onto the Gatesburg Formation residual soil. And the flow direction is shown by the blue arrow, and the white arrow indicates the recharge area on Tussey Mountain feeding the flow of this distributing stream. The red dashed circle represents the sinkhole recharge area in the stream bed, and this inset diagram shows you how it's a losing stream and it's recharging the water table out on the valley floor. It happens not only during times of snowmelt and winter runoff, but also during the summertime months due to the excess rainfall in July through December of 2018. So to summarize, the 63.75 inches of precipitation made 2018 the wettest year ever in records at the Penn State Meteorology Station. The watershed swallows 36 billion gallons of groundwater, which all became groundwater recharge, and this limited the overbank flooding of our streams in this very wettest year. So the Spring Creek Watershed has a unique combination of karst characteristics and residual soil characteristics that enabled it to swallow more